Welcome back to Chem Talk, everybody.
You bet.
The place where we break down chemistry, so it's, not so scary.
Yeah.
We're doing episode 6.2 today,
6-2.
called the Modern Periodic Table. And we're going to be focusing on how it's organized and what makes it such a powerful tool for you guys, the chemistry students out there.
You know, it's not just about memorizing a bunch of squares.
Oh, absolutely not. No way.
It's really about uncovering this hidden language of the universe.
I like that. So the periodic table, we all know it's not just a random jumble of, element squares.
Yeah.
There's definitely some method to the madness.
Absolutely.
So let's talk about how it's all organized.
Okay. So the modern periodic table it's really like a well-organized library
Okay.
where every book, or in this case element, has its own special place.
I like that.
And it's arranged by increasing atomic number,
Okay.
which is the number of protons in an atom's nucleus. And here's the really cool part. Elements with similar properties, they end up grouped together
Okay.
in vertical columns, like families with shared traits.
So like a family reunion for all the elements, like all the alkali metals hanging out,
Yeah,
comparing their, explosive reactions with water.
exactly.
Gotcha.
No, we call these vertical columns, we call them groups.
Okay.
And we'll come back to that.
All right.
But first, let's talk about the horizontal rows,
Okay.
the periods.
All right. The periods. Okay. So what makes them so special? Are they all the same?
Good question.
Do they have the same number of elements, like floors in a building?
So unlike a building, periods on the periodic table, they aren't uniform.
Okay.
They actually represent the filling of electron energy levels.
Okay.
It's kind of like adding electrons to different energy shells as we move across.
Gotcha. Okay. So the first period only has 2 elements because it's filling the first energy level, which can only hold 2 electrons. Gotcha. Okay. So periods 2 and 3 get a little bit more crowded.
You bet. Periods 2 and 3, they each have 8 elements.
Okay.
And that's because they're filling the second and third energy levels, which can hold up to 8 electrons each. So think of it like, building a house, and you're adding more rooms on each floor as you go higher.
Oh, okay. So what about periods 4 and 5? I've noticed they get a lot bigger.
Ah, that's where things get even more interesting.
Okay.
Periods 4 and 5, they jump up to 18 elements each.
Okay.
And that's because we start filling the D sublevels, which can hold up to 10 electrons. So imagine adding not just rooms, but entire wings to our house.
So we're building a mansion now
Right.
instead of just a simple house. Okay. So then periods 6 and 7 look massive.
Yeah. They're the heavyweights.
Yeah.
Periods 6 and 7 have a whopping 32 elements each.
Wow.
Because we're adding even more complex sublevels, the sublevels. It's like building a gigantic castle with hidden chambers and secret passageways.
So I'm getting the picture
Yeah.
that they get more, complex as we go down the table.
Yeah.
So how can I tell what period an element belongs to? Just by looking at it.
So you can actually determine an element's period just by glancing at its electron configuration.
Yeah.
The highest principal energy level in the configuration tells you the period number. So let's just take nickel as an example.
Okay.
Its electron configuration is Hrut 30F4
So nickel is in period 4 because of the 4 and 4 cent.
You got it.
Okay. It's that simple.
So I could do that with any element.
You could apply that trick to any element?
That's pretty handy. I'm
Yeah.
starting to feel like a periodic table pro.
Yeah.
Okay, so we've talked about periods. Now let's get back to those groups we mentioned before, the vertical columns. You said they represent elements with similar properties.
Exactly.
Okay.
And it all comes down to those outer electrons.
Okay.
The valence electrons.
Okay.
They're like the social butterflies of the atom.
They're the ones responsible for forming bonds with other atoms.
Gotcha.
And elements in the same group, they have similar outer electron configurations,
Okay.
meaning they have the same number of valence electrons that are just, eager to mingle.
Oh, so they're just looking to make connections.
Yeah.
I can see why, elements in the same group would act similarly then.
Yeah.
Now, I've seen, different ways of numbering groups. What's
Yeah.
up with that?
You're right. We actually have a couple of different systems.
Okay.
In the traditional system, which you might see in your textbooks, groups are labeled with letters A and B.
Okay.
Like 1A, 2A, and then 3A through 8A.
Okay.
And then the transition metals in the middle, they use the letter D.
Gotcha.
But internationally, the IUPAC system uses a simple numbering
Okay.
from 1 to 18, going from left to right.
So it's like different chemistry dialect.
Exactly. And it's important to be familiar with both.
Okay.
So so you don't get lost when you encounter different periodic tables.
Okay, periods, groups. Got it. Check and check.
Yeah.
Now, what about these blocks I've heard of on the periodic table?
Oh, yeah. Think of blocks as like neighborhoods
Okay.
within our periodic table city.
I like that.
They're labeled S, P, D, and F, and they visually represent which sublevel is being filled as you move across the table.
Oh, okay.
So the S block is where the S sublevel is being filled, the P block where the P sublevel is being filled, and so on.
So it's just another way of like organizing the elements
Precise.
based on their electron configuration.
Yes, but here's where it gets a little tricky. You'll notice that the D and F blocks, they're like offset
Okay.
from the main table.
Yeah.
The third sublevel actually starts filling in period 4, and the fourth sublevel starts filling in period 6.
Wait, why the shift?
So it's because the electron configurations of heavier elements, they get more complex.
Gotcha.
It's like those heavier elements needed more space
Okay.
to accommodate all their electrons. And those complex energy levels, so remember those mansions and castles we talked about?
Yeah.
Well, these are like mega skyscrapers with very intricate layouts.
I'm starting to see that it's more than just a grid
Yes,
of elements. It's like this multi-layered map
it is.
of, atomic structure and behavior.
Absolutely.
It's a lot to take in, but I'm really starting to appreciate like the elegance of it all.
And we've only just begun to scratch the surface.
Okay.
There's so much more to discover about this, fascinating tool. Actually. And in the next part of our deep dive,
Okay.
we're going to explore some of the most intriguing residents
Okay.
of the periodic table, the synthesized elements.
Ooh. Okay, so synthesized elements. Now that sounds like we're getting into some serious chemistry magic.
Yes, we are.
All right, well, we'll be right back after a quick. All right, so we've covered like the basics, periods, groups, blocks. It's all starting to make sense.
Yeah.
But now I'm really curious about these synthesized elements.
Okay.
It sounds kind of like sci-fi to me.
Well, it is pretty mind-blowing. Scientists have figured out how to create new elements, those with atomic numbers 93 and above.
Wow.
And they do it by bombarding existing elements with subatomic particles, like, tiny little bullets.
So like they're smashing atoms together
Pretty much.
to make new ones. That's so cool. But why go through all that trouble?
Because it's all about, pushing the boundaries of what we know.
Okay.
By synthesizing these new elements, scientists can explore the limits of nuclear stability.
Okay.
How atoms hold together.
Gotcha.
And who knows, maybe we'll discover some like crazy new properties and applications along the way.
So like exploring like uncharted territory on the periodic table.
Exactly.
So what are some examples of these synthesized elements? Like, have I ever encountered any of these in real life?
Think plutonium, americium, curium. They might sound exotic,
Yeah.
but they're used in things like nuclear reactors and even smoke detectors.
Really? So those weren't just like hanging out in nature. Someone actually made those.
It's wild. And the story doesn't end there.
Okay.
In 2015, 4 brand new elements were officially added to the periodic table. Nihonium, symbol NS, Moscovium, MIPPER, tennessine, Ts, and oganesson, OG.
Those names sound so cool. How do they even like come up with those?
So there's actually a whole process for naming new elements.
Okay.
It's overseen by IUPAC, the International Union of Pure and Applied Chemistry.
Gotcha.
The discoverers, they get to propose a name.
Okay.
And it's often based on, a place, a scientist, or even a mythological concept.
Oh, okay.
For example, Nihonium is named after Japan,
Okay.
where it was first synthesized.
So if they're like, officially on the periodic table now, they must be pretty stable, right?
Not necessarily. Many of these synthesized elements, especially those with like really high atomic numbers,
Yeah.
are incredibly unstable.
Okay.
Some of them exist for like fractions of a second before decaying into other elements.
So they just like appear and then disappear. How do scientists even like study them if they're like gone so quickly?
It's a huge challenge,
Yeah.
but scientists are clever.
I'm sure.
They've developed some amazing techniques
Right.
to detect and analyze these like really fleeting elements using powerful detectors to, capture those tiny signs of their decay.
Oh, wow.
It's like piecing together a puzzle with just a few like fleeting clues.
That's incredible. So are there with scientists constantly synthesizing these new elements, is there like a limit to how big the periodic table can get? Like, Could it just keep growing forever?
That's the big question, isn't it? As we move further down the periodic table, these synthesized elements become increasingly unstable.
Right.
Some scientists believe there might be like an island of stability somewhere out there.
Oh.
A region where like super heavy elements might be surprisingly stable.
An island of stability. That sounds like something I want to learn more about. Okay, so the quest to like expand the periodic table continues.
Absolutely.
Wow. Okay, so this is all so fascinating.
It is.
You know, we've explored the organization and even like ventured into like the realm of these synthesized elements.
Yeah.
But like, what does it all mean? Why should we like even care about this amazing chart of elements?
Well, think of the periodic table as like a decoder ring for the entire chemical world.
Okay.
It helps you predict how elements will behave, how they'll react with each other, and what kind of compounds they'll form.
Gotcha.
Once you understand like the language of the periodic table, you can start to understand the language of chemistry itself.
Oh, okay. So like you're saying it's like a secret key to like unlock the mysteries of matter.
You got it.
I have to admit, I'm starting to see it in a whole new light.
Good.
It's not just a boring chart on the classroom wall. It's like a dynamic, ever-evolving story of like discovery.
The story is far from over.
I bet.
We've covered a lot of ground today, but there's still so much to explore. To wrap things up, let's recap like the key takeaways from our deep dive into the modern periodic table and leave you with a question to ponder.
All right. So we've been all over the place, you know, the rows and the columns and the blocks, and we've even seen how they make these new elements. But before we go, let's just recap what we've learned about this amazing modern periodic table.
Sounds good.
Okay,
so like the modern periodic table, it's all about organization, right?
Right.
So we arrange the elements by increasing atomic number.
Yeah.
And that helps us see the repeating patterns in their properties.
Right, like those family reunions, like all the elements in a group are similar because they're, you know, in the same family.
Exactly. And remember, those similarities come from like their outer electron configuration.
Right.
Those valence electrons are what determine how elements interact.
Yeah, those social butterflies making all those connections, causing those explosions and, you know, fireworks and all the good stuff.
Yeah. Now, let's not forget those periods, those horizontal rows that tell us like which electron energy levels are being filled.
Like building a house, adding more rooms.
Yes.
I love that one.
And then we have the blocks, the S, P, D, and F blocks, which tell us which sublevels are being filled as we go across the table.
Oh, and the D and F blocks, they're like those mega skyscrapers.
Right. They're a little quirky.
Yeah, with all those electrons.
Yeah. And we can't leave out the synthesized elements. Those are like those human-made marvels that push the boundaries of the periodic table.
Yeah, it's amazing that they can actually make new elements.
I know, right?
It's like, wow, like they have the power.
I know.
To just like make stuff, make matter.
Yeah. So, you see, the periodic table, it's not just a static chart, you know?
Right.
It's dynamic and it's evolving and it shows how we are always learning new things about the elements.
Yeah, it is pretty cool.
Yeah.
And who knows, maybe they will find that island of stability.
I hope so.
Yeah. This has really opened my eyes to like the periodic table. Like it's way more than just a bunch of squares and letters.
Absolutely. It's like it's a roadmap to like understanding the elements and their behavior and how the chemical world works.
It is, yeah. So for all of you out there that are just beginning your chemistry journey, and especially those in Mrs. Williamson's class, remember, the periodic table is your friend. Don't let it intimidate you. It's all about the patterns and the quirks, you know. It's brilliant.
And never stop asking questions. Who knows, maybe you'll be the one to discover a new element. Or unlock the secrets of the universe.
You never know. Keep on exploring that chemistry, everybody. We'll see you next time.